Swayam Prabha. Digital India. Educated India.
Hello, welcome back. Today we will discuss those carbon nitrogen bond formation reaction, or more specifically carbon heteroatom bond formation reaction. The first topic that we will discuss today is the palladium catalyzed carbon nitrogen bond formation, also known as Buchwald-Hartwig coupling. Let us look at the transformation first and the generalized mechanism, and then we will discuss the role the ligand can play in these palladium catalyzed carbon nitrogen bond formation reaction. Of course, the ligand designing or ligand planning could be similar for the other carbon-carbon or carbon heteroatom bond formation reactions as well. Let us look at first the name reaction, or let us define the reaction first, what is usually called as Buchwald-Hartwig coupling. So, it is an aryl halide that is reacted with a primary or a secondary amine to get secondary or tertiary amine respectively. In presence of palladium and phosphine ligand, usually these reactions are found to be very efficient. Let us look at the name reaction. So, it is aryl halide that is reacted with an amine HNR prime and R dot. So, two different R substituent you can have a primary or a secondary amine and a palladium 0 stoichiometric amount of base that is required for these reactions, and you get AR, NR prime and R2. Okay. Of course, instead of amine one can have ROH, RSH, still it could be called as the Buchwald-Hartwig coupling reaction. In the last class we were discussing different aspects of Heck reaction, for example, and we have seen quite a few interesting topic emerging from such Heck coupling reaction. In today's class, let us first look at the catalytic cycle involved that for these palladium catalyzed carbon nitrogen bond formation reaction, and then we will try to discuss the role of ligand or how the ligand is involved during the catalytic cycle. Is it just a ligand for the metal, or ligand has conformational change that is critical for giving very high yield? That means turnover number, both turnover number and turnover frequency may also get affected by this ligand. Let us look at the catalytic cycle, and stepwise we will look at what it takes for a ligand to be efficient in this very important reaction. Also, we would like to see one example how palladium is really getting incorporated or getting started into the catalytic cycle, how palladium active species is formed during this catalytic cycle. That is also another point of interest of today's lecture. So, we will first discuss the catalytic cycle. Let us look at it. The catalytic cycle, as you know, would have the ligand palladium 0, that like similar to other carbon-carbon or carbon heteroatom bond formation reaction, it is the palladium 0 that is the active species, not the palladium 2 that may used during the reaction, but the active species should be the reduced version from there. So, that is palladium 0 should be the real active species. Let us start the catalytic cycle with palladium 0 as the starting material. So, the catalytic cycle would have ligand palladium 0, okay, and from there on the oxidative addition with ARX will gives rise to palladium 2 intermediate, where palladium 2 ARX will be present, and from there on we will have a palladium AR, NR prime and R2 will be there. Subsequently, what we will see that in this step, of course, base and amine will come into picture, H and R prime, R1 and R2 to be precise will come into picture, and we will get base plus H, of course, and then X minus, and from there on we will see a overall catalytic cycle that is producing AR, N, R prime, R2. Of course, as you can see in the catalytic cycle, we have a very generalized mechanism here. Okay. It is not stepwise, we have not drawn this stepwise yet. What we have shown is that palladium 0 will oxidatively add into ARX, then the amine will participate into the reaction, and following amine coordination and deprotonation, it will be transmetallated, so from which the intermediate will give rise to the product formation. Now, that is definitely not that very simple as I have drawn in the mechanistic cycle right now. It is little bit more complicated, actually it is much more complicated, although the transformation is very simple. One need to understand what goes on during the catalytic cycle. Before getting into that, let us try to take a look. We will come back to the mechanism and discuss stepwise little bit more, one more step at least we will add, and then we will try to look at the intricacies of the ligand design that will be involved to facilitate the each and every of these steps that is involved during this carbon nitrogen bond formation reaction. Let us look at 1-2 simple example to get the feeling what really these reactions are about. Okay. Let us look at one palladium catalyzed carbon nitrogen bond formation reaction. So, technically any aryl halide one can take. Nowadays aryl iodide, bromide, chloride, triplet, nonaphthalate, mesylate, anything can be used. That is the great application or great outreach of these carbon nitrogen bond formation reaction. Let us take a very simple reaction with aryl halide and an amine, let us say secondary amine, and let us see the product formation. So, one example, we will come back with more example in due course. We have for example, aryl chloride, of course, it is one of the most difficult substrate as one would understand, and it reacts with morpholin, and this is a pretty easy reaction for this sort of product formation. We have OMe and in this it is 90% yield, palladium is used and phosphine aryl terbutyl. So, this is not really the best ligand, but for this reaction it works quite okay and it can be done pretty easily. Of course, another type of reaction could be, so this is a very simple reaction, right. It is an aryl chloride we are looking at, and then a secondary amine. One can take even the primary amine during the reaction to get the secondary amine. So, secondary amine gives you the tertiary amine, primary amine will give you the secondary amine, right. So, any amine technically nowadays with the advanced catalytic system, advanced ligand and very highly designed ligand, one can do almost every carbon nitrogen bond formation reaction by utilizing this palladium catalyzed carbon nitrogen bond formation. Well, let us look at one heterocycle synthesis, which essentially is also an extension or the application of this method to get going the palladium catalyzed carbon nitrogen bond formation are the key step, and then we have a very interesting heterocycle formation. Okay. We will synthesize indole very simply by utilizing this approach. So, we have iodo NHR prime and an alkyne, internal alkyne for example, we take. The product we do get in these cases, if you take something like 2-iodoaniline, of course, and substituted you can have, then the product we get in this case is the indole. Okay. That is a very powerful and very simple yet very powerful reaction for this class. What is essentially happening? Of course, we need take palladium acetate in this case, 5% of it, and we take phosphine ligand and amine as base. This reaction works quite good. What definitely happening in these cases is oxidative addition is occurring to give palladium oxidative addition intermediate, and from there on what we have a beta migratory insertion. Of course, alkyne will coordinate and then will insert. So, beta migratory insertion will give you rise to this intermediate where R1 and R2 is placed in a position before the final bond formation step. So, here we do have the beta hydride elimination from here on to give you the final product. Okay. Now, what we have seen right now is if you have any iodoaniline, okay, 2-iodoaniline and substitution at any position, and if it is interacting with an alkyne in presence of palladium, then we basically will be able to ring close this one to give you the indole product formation. So, oxidative addition at the aryl iodide and then binding alkyne binding and insertion, beta migratory insertion finally will give rise to an intermediate where carbon and nitrogen bond are very close. They will undergo a reductive elimination to give you the final product formation. So, by this way indole formation is made really very easy, and one can get or one can expect the product formation quite efficiently by utilizing this palladium catalyzed carbon nitrogen bond formation process. Here carbon nitrogen bond formation process is not direct with the aryl halide, it is the aryl halide where it started, and finally alkyne gets inserted and it gives rise to the product. Well, we are little bit deviating from our major discussion today, that is palladium catalyzed carbon nitrogen bond formation. We will not discuss a lot of examples in today's class, but what we would like to discuss is why palladium is important and what oxidation state of palladium is taking part into the catalytic cycle and the role of ligand during this catalytic reaction. Let us look at the palladium salts or palladium sources that one can use for these type of reactions. So, if we are talking about R1 and R2 NH, so this is the amine, this could be primary and secondary amine for example, and for example we are taking aryl halide to give R1 R2 NAR, this is the palladium catalyzed carbon nitrogen bond formation reaction. So, what we are trying to right now discuss is during this reaction how palladium activation is happening, how do we form, how palladium 0 is formed. Okay. So, that is the main question, how palladium 0 is formed during this reaction. Of course, one can use palladium 0 complex, that we were emphasizing previously. Palladium 0 complexes are the one, let us say for example, we can have palladium 2 DVA3, we can have palladium DVA2, these are commercially available palladium 0 source, palladium PPH3-4, palladium tetrakis, but the problem is palladium 0 complexes are more active, but considerably less stable. Additionally, the residual ligands, for example, DVA or triphenyl phosphine can bind to the palladium 0 and therefore inhibiting its reactivity. Okay. So, although palladium 0 is commercially available, those we can buy such as palladium 2 DVA3, palladium DVA2 and palladium tetrakis, but in order to stabilize them we have to pay the high price. The ligand that comes with it, it does not want to go away during the reaction. So, it tries to stick around. So, for example, DBA tries to stick around, phosphine, triphenyl phosphine tries to stick around. But those ligand we are not very much interested in during the reaction, although to stabilize starting material that is essential, but during the reaction we want one of our sophisticated ligand which is very efficient, which can give very high turnover number and turnover frequency, but those ligand placement at the palladium center becomes very difficult. And therefore, although palladium 0 is active, but they are of course less stable compared to palladium 2, but still people want to have palladium 2. Okay. What are the palladium 2 sources we are usually using? Let us look at that. Palladium 2 salts, we have seen the examples with it previously, but to put it in the perspective, palladium acetate usually we use, a lot of people use allyl palladium chloride, a dimer species, or acetonitrile, bis-acetonitrile palladium chloride. Of course, palladium 2 salts are very stable, all of them, but must be reduced to palladium 0 by heating in presence of additives of, for example, phenyl boronic acid, amine as we have seen in the last class, or phosphine. We have not seen the example of phosphine when it is used to reducing the palladium 2. So, there exists a number of method that utilizes the in situ reduction of palladium 2 to palladium 0 formation. However, those methods, few of them only we have seen. In one case, for example, when we were discussing about the Kumada coupling, organolithium reagent was used, or the reagent that is used for the reaction is participating in situ to reduce palladium 2 to palladium 0, that we have seen. In the last class, we have seen also how amine can be participating by beta hydride elimination to reduce the palladium 2 to palladium 0. In today's class, now we are going to see how phosphine can be involved. Phosphine, the ligand itself, the ligand which we need for our precious palladium catalyzed different coupling reaction, for example, carbon nitrogen bond formation reaction, the ligand used in the reaction will be used or can be used as a reducing agent for palladium 2 to palladium 0 formation. Let us look at how this reaction works, because in almost essentially every cases one uses palladium acetate or palladium chloride or palladium allyl palladium species, which are essentially palladium 2 species, which cannot be the real active species. The real active species must be palladium 0. So, therefore, how they are forming in the reaction, that is essential to see. Let us look at the process how phosphine is reducing palladium 2 to palladium 0. Okay. So, we are talking about palladium activation. How do we form palladium 0? So, what exactly we take, for example, is we take the phosphine ligand, 2 equivalent of phosphine, and we put palladium 2 salts, and that is, for example, palladium acetate we end up taking. It is a reversible reaction. We do see the binding of it. So, diphenyl, for example, 2 phosphine ligand binds with palladium 2 to give palladium diacetate intermediate, and from there on it is the formation of a cationic and anionic species that is critical, for example, palladium 0 and then this acetate intermediate. This should be a negatively charged intermediate along with ACOPR3 plus, this is a cationic intermediate. So, essentially one of the phosphine over here and one of the acetate decides to leave the coordination site from the palladium. So, it is acetoxyphosphine that is formed, that is a cationic species, and accordingly it is now a palladium 2 species to palladium 0 formation, where acetate is coordinated. This got to be an anionic intermediate from which water participates. So, trace amount of water is always good for this reaction, and we need acetic acid for the reaction as well. Overall, so this acetate and both the acetate forms the acetic acid, the phosphine now. So, the proton comes from the water for both of those acetic acid formation, the oxygen that from water gets into phosphine to give rise to the phosphine oxide species, as well as where we have now one of the phosphine incorporated into the palladium to give the palladium 0. So, what we have just now seen is then 2 equivalent of phosphine ligand, which is very precious of course, 2 equivalent of phosphine ligand participating in reacting with palladium. The palladium oxidation state is palladium 2. So, 2 of those phosphine ligands bind with one of the palladium, along with it palladium has 2 more acetate, of course, it is a palladium 4 coordinate now. What happens from there is one acetate and one phosphine leaves the coordination site to form a cationic intermediate, and that leaves the palladium in palladium 0 state along with the acetate coordinated with it. So, it is an anionic intermediate. So, cation and anion formation. So, it is like almost a ion pair formation happens right over there in presence of catalytic amount of water. Finally, what we see that a phosphine oxide is formed during the process, okay, and that leaves out to the, and that gives rise to yet another equivalent of the palladium phosphine complex. So, 2 phosphine ligand react with one palladium to give one phosphine, one palladium species. That is the real active species. Palladium is in now 0 state, and in the process trace of phosphine oxide that gets going during the catalytic cycle. Now, that is why, that is also explain why we usually use 2 equivalent of phosphine and 1 equivalent of palladium during the reaction, right. Often we see that 10 mole % for example palladium and 20 mole % of ligand, that is a lot, but that is how it may be involved during the catalytic cycle. So, 1 equivalent of phosphine ligand usually, if it is a bulky one, is good enough for the real catalytic species, but another equivalent goes on activating goes for activation of this palladium 2 to palladium 0. We will see much more of those activation little later on, but now we must see the stepwise mechanism of the palladium catalyzed carbon nitrogen bond formation, or before getting into that, let us look at the various ligand that might will be involved during the palladium catalyzed carbon nitrogen bond formation reactions. So, various ligand that is involved during the palladium catalyzed carbon nitrogen bond formation reaction. So, the reaction we are interested in is this X. Okay. Now, these X are very useful aryl halide, and we are looking at H, N, R and R prime. Okay. We are of course palladium 0 as the catalyst, palladium 0 and ligand we are taking base and solvent are of course there. What we get is N, A, R and R prime, this is the species. The ligand that is one of the most popular, we are now going to draw different ligand that might will be involved. So, today's class will be mainly ligand centric, how ligand is participating into the catalytic cycle. In one case we will be discussing today, and we have different R group in here. So, we have a biaryl. So, this is a biaryl phosphine ligand. There are substituent at various positions of this phosphine ligand. So, these are the ones which is used by Buchwald, and the famous ligands are for example Rufos, John Phos, X Phos of course and S Phos, etc. The other series of ligand which is ferrocene based ligand is popularized by Hartwig group. What we see is also it is not a monophosphine containing, this is a monophosphine containing bulky phosphine ligand, but this is a bisphosphine or bidentate chelation. Okay. Usually the Josephus version of it anyway. So, this is popularized by Hartwig. Okay. A reference one must write down Jacks for example 2008 130 6586, all right, that is fine. So, these are the ligand that is used for these processes. So, there are plenty of other ligands that is also involved, we will discuss soon. So, what we have seen is a biaryl phosphine ligand that is good for these purposes. We have also seen this ferrocin based ligand which is involved during the catalytic cycle. Let me draw few more ligands which are very popular in this field, specifically the carbene based ligand. Not only the phosphine ligand, monodentate phosphine, we have seen biaryl phosphine, we have seen the bidentate phosphine which is very popular and very useful. Also the nowadays we do know that there are carbene ligand which is useful and very effective for this reaction as well, and there are also Baylor's ligand, there is also Kong's ligand, there is Vercade's ligand. So, lot of different people have come up with a variation of these ligands and which are found to be quite efficient, but perhaps the most efficient remained are the biaryl phosphine ligand that we will be discussing in a moment, how these reactions are affected by various ligands and what might will be one of the criteria to design the ligand in order to get the high selectivity and high efficiency of these palladium catalyzed carbon nitrogen bond formation reactions. The other ligand that is involved in this process are the carbene ligand, where you do have these isopropyl group. So, SIPR, SIPR ligand, okay, of course, by Herman and Nolan. These ligands are developed and put forward. So, we have isopropyl on the both side, and these are the carbene based ligand by Herman and Nolan. You can have a reference, JAX 2006 128 4101. Of course, there are Kong's ligand which is also very popular. We have Vercade's ligand. Let us look at the Kong's ligand. These are again based on monodentate phosphine ligand, but these are indole based, quite efficient again. So, this is Kong's ligand. We have Baylor's ligand which are again heterocycle based. These are the again very effective ligand as well. So, we have seen what we have seen so far in today's class. Then for palladium catalyzed carbon nitrogen bond formation reaction, we use palladium 2 salts usually. Palladium 2 salt can be in situ converted to palladium 0 by sacrificing one equivalent of phosphine ligand which gets oxidized to phosphine oxide, and in the process palladium 2 is reduced to palladium 0. Water is needed, catalytic amount or water is needed for this palladium 2 activation to give rise to the palladium 0 species. So, 2 equivalent of ligand is utilized for the process, one equivalent gets going with the palladium, another equivalent is sacrificed for phosphine oxide formation. So, palladium 2, although it is in +2 oxidation state, it is reduced in situ to palladium 0. The readily available palladium 0 salts are not a great source for the palladium catalyzed reaction, because they usually comes with their own ligands such as DBA and triphenyl phosphine, which are not the best ligand one can have for the various carbon heteroatom and carbon carbon bond formation reaction. So, one must use palladium 2 without a strong coordinating ligand, or which will not be good for the catalytic cycle. Now, we have also seen how the palladium catalysis is used for carbon nitrogen bond formation reaction. We have seen the overall simplified mechanistic side. We will be discussing more about the ligand, how ligand is important into this palladium catalyzed carbon heteroatom or in general any cross coupling reaction, and what is perhaps one of the criteria. We will take a case study, specifically we will discuss the biaryl phosphine ligand which is developed by Buchwald group at MIT, and then we will try to discuss the aspects of this ligand that is crucial for promoting high efficiency for these reactions. So, we will come back with that in the next class. Keep studying about these different metal catalyzed bond formation reactions. Bye bye.